In 1981, a team of astronomers pointed their instruments at a patch of sky and found something that should not exist. Not an unusual galaxy, not a strange signal, not a new type of star or a distant object behaving in unexpected ways. What they found was the opposite of something, a region of space enormous, incomprehensible in scale, that contained almost nothing at all. They checked their equipment, they rechecked it, they reviewed the methodology, looked for errors in the data, considered every explanation that didn't require them to believe what they were seeing. And one by one, every alternative fell apart. The emptiness was real. What sits 700 million light-years from Earth, in the direction of the constellation Boötes, the herdsman, is one of the largest known structures in the observable universe. Not a structure made of matter, a structure made of absence. A bubble of void so enormous that crossing it at the speed of light would take 330 million years. A place so empty that when astronomers fully grasped its size, one of them made an observation that has never quite left the literature since. If Earth had been located at the center of the Boötes void, not near it, not at the edge of it, but at the center, humans would not have discovered any other galaxy until the 1960s. The nearest neighbors would have been so distant that every telescope we built before the mid-20th century would have looked out in every direction and found only darkness. No galaxies, no clusters, no evidence of a universe beyond our own. We would have looked out at all of existence and concluded we were alone. Not just on this planet, in all of space. That is the scale of the place we are talking about. But here is what you should actually hold on to. Because the size of the Boötes void, while staggering, is not the most unsettling thing about it. Scientists can process large numbers. They can accommodate enormous scales. The universe is full of things that are very, very big. What unsettles cosmologists about the Boötes void is not how large it is. It's that it should not exist at all. By every model we have of how the universe organizes itself, models that have been tested, refined, confirmed by decades of observation across billions of light years, a void this size is not supposed to be possible. The universe has not been around long enough to produce something this empty, this large, through any process we currently understand. And yet, there it is. It's not the size that should disturb you, it's what the size implies. And to understand that, we have to start at the beginning, not of the void, but of everything. The universe, at its largest scales, is not random. This is something that took astronomers a long time to fully appreciate. For most of human history, when we looked at the sky, we saw points of light scattered in patterns that seemed arbitrary. Constellations were stories we told ourselves to make sense of randomness. And for a long time, it seemed reasonable to assume that at the largest scales, the universe was more or less uniform. Matter spread out in all directions, roughly even, filling space like a gas in a container. That picture was wrong. When astronomers began to map the positions of galaxies not just in 2 dimensions, as they appear on the sky, but in 3, accounting for their distances from us, something remarkable appeared. The universe is not a fog. It is a web. Galaxies cluster. They gather along thin filaments of matter, enormous invisible threads stretching hundreds of millions of light years across the sky. Where these filaments intersect, the densest concentrations form. Galaxy clusters, places where hundreds or thousands of galaxies orbit each other in a knot of gravity, where the gas between galaxies is so hot it glows in X-ray light, where some of the most violent events in the universe take place. Quasars, colliding galaxies, black holes consuming matter so fast they outshine entire star systems. And between the filaments, the voids, regions where galaxies are sparse, where matter has drifted away, pulled toward the filaments by gravity, leaving behind a relative emptiness. These voids are not unusual. They are a normal and expected feature of the cosmic web. Every large-scale map of the universe shows them, irregular bubbles of low density, surrounded by walls and filaments of higher density, like the holes inside a foam sponge. Most cosmic voids are between 20 and 150 million light-years across. Some are larger. A few push toward 200 million light-years. They are notable, they are studied, but they fit more or less within the range that our best models of the universe can produce. Given 13.8 billion years, the interplay of gravity, dark matter, and the expansion of space should naturally generate exactly this kind of structure. Walls and filaments on one hand, voids on the other, a hierarchy of empty and full stretching across the entire observable universe. The models work. They have been tested against observations again and again, and they hold up. The Boötes void is 330 million light-years across. Not 150, not 200, not even a borderline case that pushes the upper edge of what the models can accommodate. 330 million light-years, more than twice as large as any void the standard models comfortably explain. A structure so far outside the expected distribution that when it was first confirmed, cosmologists had to sit with the uncomfortable possibility that something was wrong, either with the models, or with their understanding of the universe's history, or with something deeper still. To give you a sense of what 330 million light-years actually means against the backdrop of the universe, the observable universe is roughly 93 billion light-years in diameter. The Boötes void alone accounts for more than 0.3% of that total span. That sounds small, but the observable universe contains an estimated 2 trillion galaxies. The Boötes void, which should contain roughly 2,000 of them based on the surrounding density, contains 60 galaxies, where there should be 2,000. And even those 60 are not scattered evenly through the interior, occupying the void the way you might expect a small number of things to spread out through a large space. They are clumped, huddled, gathered in a faint, thin filament that runs through part of the void's interior, as if the cosmic web, which governs the entire rest of the universe, made one hesitant, half-hearted attempt to reach into this place, and then gave up. And yet, nothing else is there, or almost nothing, because the full strangeness of what those 60 galaxies represent, and what they don't represent, is something we need to spend some time with. Robert Kirshner did not set out to find the Boötes void. In 1981, Kirshner was a young astronomer at the Harvard-Smithsonian Center for Astrophysics. He and his colleagues, Augustus Oemler Jr., Paul Schechter, and Stephen Schechtman, were engaged in what was, by the standards of observational astronomy, fairly routine work. They were conducting a systematic survey of galaxies in a selected region of the sky, measuring their positions and distances, trying to build a more accurate picture of how galaxies were distributed in three-dimensional space. The method was careful and methodical. They would target a region, observe the galaxies they could detect, measure the redshift of each one, the degree to which its light had been stretched toward the red end of the spectrum by the expansion of the universe, which tells you how far away it is, and plot its position in space. Repeat for thousands of galaxies. Build the map piece by piece. Then, in one part of their survey region, the galaxies stopped. Not thinned out, not gradually became sparser the way you'd expect near the edge of a cluster. They simply stopped. A region of space that should have contained dozens or hundreds of galaxies, based on the density of everything around it, contained exactly 0. The team did not announce this immediately. They checked. They checked again. They considered whether there was something wrong with their instruments, something biasing their measurements, some systematic error that had created an artificial hole in their data. They found nothing wrong. The instruments were working correctly. The methodology was sound. The emptiness was real. When Kirshner's team published their findings, the initial reported diameter of the void was approximately 300 million light-years. The paper was immediately recognized as significant. Other astronomers turned their instruments toward the same region, conducted their own surveys, looked for any reason to question the result. They couldn't find one. Every survey confirmed the same thing. There was a vast, largely empty region of space in the direction of Boötes. And as survey technology improved over the following decade, as redshift measurements became more precise and astronomers were able to probe deeper into the region, the true picture became clearer and larger. The void extended further in some directions than the original survey had captured. Its shape, it turned out, was not a clean sphere but an irregular three-dimensional structure, elongated, slightly distorted, its boundaries ill-defined in places where the transition from emptiness to the surrounding universe was gradual rather than sharp. Some analyses placed its diameter closer to 330 million light-years. A few pushed higher, and the zero galaxy count from the original survey was revised. Not in the reassuring direction. 60 galaxies, scattered through an interior that, by all cosmological expectation, should host closer to 2,000. 60 where there should be 2,000. And those 60 galaxies are not just few in number. They are strange in their arrangement. They are clustered into a thin filament-like structure, a ghostly echo of the cosmic web that governs everything outside the void. As if the universe tried to write its normal pattern into this place, managed only a faint suggestion of it, and then found itself unable to complete the work. What they found in the years after the initial discovery made the original finding look almost modest. Because once the size of the Boötes void was confirmed, astronomers found themselves confronting a question that the data had no clean answer to. If the Boötes void is genuinely this large and genuinely this empty, then either our models of the universe are missing something, or the universe is doing something we haven't understood yet. What they found next made the original discovery look small. To understand why the Boötes void troubles cosmologists so deeply, you have to first understand what the universe looks like everywhere else. In a typical region of space the size of the Boötes void, 330 million light-years across, there would be, on average, somewhere between 1 and 2,000 galaxies. Not all of them large. Many would be dwarf galaxies, small, irregular collections of a few billion stars, faint and dim. But mixed among them would be spirals comparable to our Milky Way, elliptical several times its size, and the occasional giant, enormous elliptical galaxies containing trillions of stars, presiding over their local neighborhoods like vast, slow-spinning engines of gravity. All of those galaxies would contain stars, hundreds of billions of them each in many cases, and around those stars, planets, rocky planets and gas giants and icy moons. The full chemical richness of the universe, hydrogen and helium from the Big Bang, carbon and oxygen and iron forged in stellar cores and scattered by supernovae, would be working its way through those systems, building complexity, enabling chemistry, making possible the slow accumulation of structure that we call, when it goes far enough, life. In the Boötes void, none of that is happening, or almost none of it. 60 galaxies cannot produce anything approaching the complexity of a normal region of space. The void is not simply empty of galaxies. It is empty of what galaxies make possible. The stellar evolution, the supernovae that enrich the interstellar medium with heavier elements. The generations of stars that must live and die before the conditions exist for planets like Earth to form. The slow, patient process by which matter organizes itself into something capable of asking questions about its own existence. In the Boötes void, that process is either running at a fraction of its normal rate or effectively absent. Now here is the question that sits at the center of all of this. The universe is 13.8 billion years old. In that time, the forces of gravity, dark matter, and cosmic expansion have worked together to produce the structure we see. The cosmic web, the filaments and clusters and walls of galaxies, the voids between them. This process is called large-scale structure formation, and the models we have built to describe it, based on the physics of the Big Bang, the nature of dark matter, and the equations of general relativity, are among the most successful in all of science. They match observation after observation. They predict the distribution of galaxies with remarkable accuracy across enormous swaths of the observable universe. But when those same models try to produce a void the size of the Boötes void, when physicists run their simulations of the universe from the Big Bang forward and look for structures this empty, this large, they struggle. The standard models of structure formation, using the best available values for the age of the universe, the density of matter, and the properties of dark energy, simply do not readily generate an emptiness this extreme in the time available. The universe is too young. Gravity has not had enough time to evacuate a region this large to this degree of emptiness. The physics, as we currently understand it, suggests the Boötes void should not look the way it does. And so scientists asked the only logical question: where did it go? When the universe doesn't match the models, you don't throw out the models. Not immediately, not without exhausting every alternative. You build hypotheses. You test what you can. You argue about the rest. And you try, through the slow, difficult, often frustrating process of science, to find the explanation that accounts for everything you're seeing without requiring you to abandon everything you already know. The Boötes void generated a significant number of hypotheses over the decades following its discovery. Some were conservative, slight adjustments to existing theory. Some were more speculative. And a few sat at the outer boundary of what mainstream cosmology was willing to take seriously. The first and most restrained explanation was this: the void is an illusion. Not deliberately, not a hallucination or an error, but a statistical artifact of perspective. When you observe the universe from a single point, which is, of course, the only option available to us, there are certain configurations of matter that can appear from your specific vantage point to create a false impression of a large empty region. Multiple smaller voids, each individually explained by ordinary physics, that happen to lie along the same line of sight from Earth, stacking up to create the appearance of one enormous gap. This explanation was appealing because it required no new physics. It asked only that we accept the void as a trick of geometry. Several smaller absences, viewed from the right angle, masquerading as one impossible large one. The problem was that follow-up surveys, conducted over many years with improving technology, examining the void not just in the radial direction from Earth but across its full three-dimensional extent, did not support this interpretation. The Boötes void appeared to be a genuinely coherent structure in three-dimensional space. The emptiness was real in all directions, not just along our line of sight. Ruling out the perspective explanation did not happen quickly or dramatically. It happened the way most things happen in science, through the slow accumulation of evidence that made the alternative progressively harder to defend. The second theory involved dark energy. Dark energy is the name we have given to whatever is causing the universe's expansion to accelerate. It was discovered in 1998, an observation so unexpected that the physicists who made it initially questioned their own data, and it has been confirmed by multiple independent lines of evidence since. Something is pushing the universe apart, faster and faster, and we do not know what it is. Dark energy is a placeholder, a label on a mystery. One possibility raised in the context of the Boötes void was that dark energy might not be perfectly uniform, that it might vary in density across the universe, stronger in some regions, slightly weaker in others. If that were true, then regions where dark energy was more concentrated might expand faster than average, driving matter away more aggressively and creating voids larger and emptier than the standard models, which assume dark energy is uniform, would predict. This idea was scientifically tractable. It was testable, at least in principle. If dark energy were inhomogeneous, the signature should show up in other observations: the distribution of galaxies at very large scales, the behavior of the cosmic microwave background, the way light from distant supernovae is stretched. Researchers looked for those signatures. The results were mixed. There were hints in some datasets of large-scale variations in the expansion rate, but no definitive evidence of the kind of dark energy variation that would be needed to explain the Boötes void. The theory remained plausible, but unconfirmed. The third explanation went further back, all the way to the beginning. In the first fractions of a second after the Big Bang, the universe was an environment of almost incomprehensible density and energy. Quantum fluctuations, the random, probabilistic variations in the density of energy that are a fundamental feature of quantum mechanics, were imprinted on the fabric of space at that moment. Those fluctuations, stretched to cosmic scales by the rapid expansion of the early universe, became the seeds of all the structures we see today. The subtle variations in density from the Big Bang grew, under the influence of gravity, into the galaxies and clusters and voids of the cosmic web. Some researchers proposed that the Boötes void might trace back to an unusually deep underdensity in the early universe. a quantum fluctuation more extreme than typical, a region where, in those first fractions of a second, the density of matter happened to be significantly lower than its surroundings. Over 13.8 billion years, that initial deficit would have compounded. Matter that was already slightly absent would have been increasingly drawn away by the gravity of the denser regions surrounding it, leaving behind an emptiness that grew and deepened with time. The problem with this explanation was not that it was impossible. It was that it was implausible. The fluctuation required to produce something the size of the Boötes void, that empty over that many years, would sit so far out on the statistical tail of what quantum mechanics predicts that its existence in our observable universe would itself be surprising. Not ruled out, but uncomfortable. The kind of explanation that, when you invoke it, leaves a quiet unease in the room. You have explained the anomaly by pointing to a different anomaly. And there was a fourth theory, one that sat further from the mainstream than the others and that most cosmologists were reluctant to engage with directly, but that a small number of researchers returned to carefully in the years following the void's discovery. The idea that the Boötes void might be connected to something in the very early universe that left a mark not just on the distribution of matter, but on the light itself. Every single one of these theories had a problem. None of them had a fatal flaw. None of them could be definitively ruled out, but none of them fully closed the case either. Each one left a gap, a place where the explanation strained under the weight of what the observations actually showed. And then something happened that changed the conversation entirely. In 2003, NASA launched a satellite called the Wilkinson Microwave Anisotropy Probe, WMAP as it was known. Its purpose was to map the cosmic microwave background, the faint afterglow of the Big Bang that fills the entire sky, a snapshot of the universe as it was roughly 380,000 years after its birth, when matter and light first separated and the universe became transparent. The cosmic microwave background is one of the most important things in science. It is the oldest light we can see. It carries within it the imprint of conditions in the very early universe, the pattern of density fluctuations that seeded all the structure that followed. Reading it carefully is like reading the opening sentence of the story of everything. WMAP mapped that light with extraordinary precision. And in 2004, scientists analyzing the data noticed something unusual. There was a cold spot, a region of the microwave sky significantly colder than its surroundings. We are talking about a difference of roughly 70 millionths of a degree Celsius. In absolute terms, that is nothing. But in the context of the cosmic microwave background, where the entire sky varies in temperature by only tiny fractions of a degree, a cold spot of that magnitude and that size was statistically notable. The probability of it occurring by random chance within the standard model of the early universe was estimated by some analyses at roughly 1 in 200,000. Not impossible, but remarkable. Cold spots in the CMB are not in themselves surprising. They correspond to regions of slightly lower density in the early universe, the precursors of the voids we see today. When the CMB photons from those regions traveled toward us, they had to climb out of slightly shallower gravitational wells, gaining a small amount of energy that, under normal circumstances, balances out. But in a universe with dark energy, with an accelerating expansion, that balance breaks down slightly. Photons traveling through large voids lose a tiny bit of energy, and that energy loss shows up in the CMB as a cold spot. This effect has a name, the integrated Sachs-Wolf effect. And in principle, it means that the largest voids in the universe should leave faint cold imprints on the microwave sky. When researchers made this connection, a question immediately arose. The CMB cold spot discovered in the WMAP data was unusually large, unusually cold, and its location in the sky was not inconsistent with the direction of the Boötes void. Could they be the same structure seen in two different ways? The void as we observe it today, a 330 million light-year bubble of emptiness in the distribution of galaxies, and the cold spot, a faint mark on the oldest light in the universe, imprinted by the same primordial underdensity as it evolved, over billions of years, into the void we now measure. If the connection were real, the implications would be significant. It would mean the Boötes void was not a random anomaly, not an unlikely fluctuation or a statistical accident or a trick of perspective. It would mean the void was written into the universe from the very beginning, seated in the quantum fluctuations of the first moments after the Big Bang, imprinted on the light that filled the early universe, and then slowly, over 13.8 billion years, emptied out into the structure we observe today. It would mean the void was not a mistake. It was a feature. The debate over this connection has never been fully resolved. Some analyses find statistical support for a link between the CMB cold spot and the large-scale structure in the Boötes region. Others find the connection too weak to be confident. The CMB cold spot itself remains a subject of active discussion. Its origin is debated, its statistical significance is debated, and the question of whether it represents something new and unexplained, or simply a rare but ordinary fluctuation in a universe large enough to contain many rare things, has not been definitively answered. But the possibility sits there quietly in the literature. Two anomalies, two things that don't quite fit the standard picture, sitting in the same part of the sky, separated by billions of years of cosmic time, possibly whispering the same story at different scales. And then the conversation shifted again, because while some researchers were asking whether the Boötes void was connected to the ancient light of the Big Bang, another group was asking a different kind of question entirely. Not what the void is, but what it does. The cosmic web is not a metaphor. It is a real physical structure, a three-dimensional network of filaments made primarily of dark matter. Matter that we cannot see, cannot detect directly, cannot observe with any instrument we currently possess, but whose gravitational influence is written across the entire visible universe. The dark matter filaments are the scaffolding on which everything we can observe is built. Along those filaments, ordinary matter accumulates. Gas clouds collapse under gravity. Stars ignite. Galaxies form and grow and evolve. The web is the skeleton of the universe. Every star you have ever seen in the night sky, every galaxy in every deep field image, every structure at every scale we have ever mapped, all of it lives along the threads of the cosmic web. Where filaments intersect, the density is highest. These are the galaxy clusters, the cities of the universe, where hundreds or thousands of galaxies move through a common gravitational field, where the gas between galaxies is heated to millions of degrees by the energy of infalling matter, where black holes at the centers of galaxies grow to billions of solar masses, where the most energetic events in the universe occur on a regular basis. And between the filaments, the voids, here is something that is not widely appreciated, and that changes the way you think about the Boötes void. Voids are not passive. They are not simply holes where nothing happens. They are dynamic regions of the universe where space itself expands faster than the average, because there is less matter to slow the expansion down. A void pushes. It drives matter outward along its walls. It is, in a real physical sense, an engine, an enormous region of below-average density that accelerates the expansion of space within its boundaries, feeding the filaments and clusters that border it, contributing to the flow of matter that gives the cosmic web its structure. Think about that for a moment. The emptiness is not the absence of structure. The emptiness is part of how structure forms. The void drives matter toward the filaments. The filaments shape the boundaries of the void. The two are not opposites. They are partners in the same system. The cosmic web is held together not just by the gravity of the matter it contains, but by the outward pressure of the voids that separate its components. Remove the voids and the filaments would not look the way they do. Remove the filaments and the voids would not be bounded the way they are. The Boötes void, in this framework, is not a failure of the universe to produce structure. It is one of the forces that produced the structure around it. A 330 million light-year engine of expansion, pushing matter outward in all directions, feeding the walls and filaments that surround it, shaping the local universe through the force of its own emptiness. There is something worth sitting with in that idea. The great void is not passive. The emptiness acts. But this framework also sharpens the central problem. Because if the Boötes void is simply doing what all voids do, expanding, pushing, shaping the structure around it, then it is, in a sense, a normal phenomenon. Just much, much larger than normal phenomena are supposed to be. And if the physics of voids is the same at 330 million light-years as it is at 50 or 100, then the question of why the Boötes void is so large is not answered by understanding what voids do. It is only sharpened. Why does the machinery of the cosmic web produce, in this one place, a void more than twice the size that the best models predict should be possible? Is there a process at work inside or around the Boötes void that current cosmology has not fully captured? A mechanism of structure formation that operates differently at very large scales? A feedback loop between the void's expansion and the surrounding filaments that amplifies its growth in ways the models don't account for? Or is the Boötes void doing something simpler and more unsettling, telling us that our understanding of how the universe evolved is incomplete in a way that matters? Which raises a question no one has been able to fully answer. There is another way to think about the Boötes void that has nothing to do with cosmological models. Think about signals. Every communication we have ever sent into space, every radio broadcast, every television transmission, every radar pulse and deliberate transmission and accidental electromagnetic leak from a century of technological civilization travels outward from Earth at the speed of light. Those signals have been spreading through space for roughly 100 years. They have filled a sphere of space approximately 200 light-years in diameter. In cosmic terms, that is nothing. A single grain of sand on a beach that stretches to the horizon in every direction. The nearest star to our Sun is 4.2 light-years away. The center of the Milky Way is 26,000 light-years away. The nearest large galaxy is 2.5 million light-years distant. Our signals have barely left the neighborhood. Now imagine a civilization in the Boötes void. A civilization with 1 billion years of technological development behind it. A civilization sitting in one of the 60 galaxies scattered through that vast interior emptiness. A civilization that has long since solved the problems we are still struggling with: energy, computation, communication across interstellar distances. A civilization capable of sending signals between galaxies. From inside the Boötes void, the universe looks different. Look outward from any position in the void's interior and you see, in most directions, very little. The nearest galaxies outside the void are hundreds of millions of light-years away. In the directions that lead toward the interior of the void, there is almost nothing between you and the boundary, and beyond the boundary, the filaments and clusters of the cosmic web appear as a distant shell of brightness, a ring of structure surrounding an enormous surrounding darkness. A civilization in the Boötes void, studying the universe around it, would have arrived much later at the conclusion that other galaxies exist. Their sky, even through powerful telescopes, would have been sparser in most directions. The cosmic web, so apparent from our position embedded within a reasonably populated region of the universe, would have looked to them like a distant wall, a bright perimeter around an enormous interior emptiness. They would have known, eventually, that they lived in an unusual place, a place the universe had chosen, for reasons their physics would struggle to explain, to leave nearly empty. And if they sent signals in any direction toward any neighbor, those signals would travel for hundreds of millions of years before reaching the nearest populated region of the universe, before reaching the nearest galaxy cluster, the nearest place where stars are abundant, the nearest place where the conditions for complexity are routinely available. A signal sent from the Boötes void toward Earth, if sent today, would arrive roughly 700 million years from now. When it arrives, whatever is living on this planet, if anything is, will have had 700 million years of evolution beyond what we are now. And a reply sent back would take another 700 million years to return. The round-trip time for a conversation across the Boötes void, in the best case, is 1.4 billion years. There is a silence at the heart of the Boötes void that goes beyond the absence of galaxies. It is the silence of time, of distance, of a kind of isolation that is qualitatively different from any isolation we have ever experienced or imagined. Not the isolation of a remote island or a distant planet, or even a far-flung star system in the outer reaches of a galaxy. But the isolation of an entire region of the universe, separated from the nearest populated areas by hundreds of millions of light-years of expanding space. We have spent decades listening to the sky for signals from intelligent life. The search has been long and, so far, unrewarded. Many explanations have been offered for why we have heard nothing: the distances involved, the brief windows during which civilizations might be transmitting, the possibility that other forms of communication make radio obsolete, the possibility that we are rare. But the Boötes void adds a dimension to that silence that is worth considering. Even if something exists in the void, even if 60 galaxies are enough to produce, somewhere, the conditions for life and intelligence and civilization, the silence from that direction would be expected. Not because nothing is there, but because the distance is so extreme that reaching us would be, by any definition of the word, almost impossible. The silence from the Boötes void is a particular kind of silence. It is the silence of a place that, even if it is speaking, cannot be heard. And that silence, it turns out, may not be accidental. The edges of the Boötes void are not a clean border. Space does not draw sharp lines. The universe does not go from empty to full the way a wall goes from one side to another. The transition from the interior of the void to the surrounding universe is gradual. A slow thickening of galaxies, a gentle increase in density, a quiet return to something resembling the normal texture of the cosmos. But those edges are scientifically interesting in their own right, because the boundary of a void, any void, not just the Boötes void, is where some of the most intense processes of galaxy formation and evolution occur. Here is why. As the void expands over cosmic time, it drives matter outward. The galaxies and gas and dark matter that might have populated the void's interior instead accumulate along its walls. They pile up, they compress, and in those high-density regions, the boundaries between the void and the surrounding universe, the rate of star formation can be significantly elevated. The collision of material from the expanding void with the surrounding cosmic web creates conditions where galaxies interact more frequently, where gas clouds collapse into stars more readily, where the universe is actively, visibly, dynamically constructing itself. The walls of a large void are busy places. Along the boundaries associated with the Boötes region, astronomers have found exactly this kind of elevated activity. Dense galaxy groups, long filaments connecting to larger structures, the familiar architecture of the cosmic web, but concentrated, compressed, enriched by the pressure of the void at its back. But some of what has been found along these edges is less easy to categorize. There are galaxy configurations whose shapes appear distorted, stretched or compressed in ways that suggest they have been influenced not just by the gravity of nearby matter, but by the geometry of the void itself. Galaxies whose orientations, whose alignments, whose positions in space seem to reflect the outward pressure of the expanding emptiness behind them, as if the void has not simply pushed matter to its edges, but left a structural signature in the way that matter has arranged itself. There are also galaxies along the boundaries of the Boötes region that appear more isolated than their environments would predict. Galaxies that have somehow missed the filaments, that sit in relative solitude even in regions where the density should be high enough to pull things together. Their existence is not impossible to explain, but it is not immediately comfortable either. And there are the questions, still open, still debated, about what the structure of the void's walls tells us about the void's history, about how long it has been expanding, about whether its current size is consistent with what the standard models predict it should have reached in 13.8 billion years, or whether it has grown faster than expected, about whether the walls show evidence of the kind of matter accumulation you would expect from a void of this age and size, or whether the picture is more complicated. The Boötes void, even at its edges, leaves questions. Not dramatic questions, not the kind of questions that make headlines or force a crisis in cosmology, but the kind that sit in papers and conference talks and become footnotes in the ongoing conversation that science has with itself about what it knows and what it only thinks it knows. Some of what it produced at the very edges where the void meets the web, some of it shouldn't exist in quite the form it does. Not dramatically, not in ways that overturn anything, but in ways that are noted, that are discussed, that are left open in the literature for the next generation of observations to address. The Boötes void, from its interior to its edges to the structures that border it, remains a place that resists complete explanation. There is something that happens when you sit with the idea of the Boötes void long enough. The numbers stop being numbers. 330 million light-years stops being a measurement and becomes something more like a feeling. The weight of the emptiness, not threatening, not malevolent, just vast and old and indifferent to everything we have ever thought or built or cared about, settles into the background of whatever you are thinking about. It is worth taking a moment to remember where we are. We exist in a reasonably populated corner of the universe. Our sun is one of roughly 200 to 400 billion stars in the Milky Way, a large spiral galaxy about 100,000 light-years across. The Milky Way is part of the local group, a collection of more than 50 galaxies bound together by gravity into a common structure roughly 10 million light-years in diameter. The local group is a small part of the Virgo supercluster, which is itself a component of the Laniakea supercluster, a structure 500 million light-years across that contains the equivalent mass of 100 million billion suns. We are, in the language of the cosmic web, well connected. There is matter around us in all directions. The filaments reach us. The web is dense where we are. Not everyone gets that. Not everywhere in the universe is like this. The Boötes void is the reminder that the abundance we take for granted, the stars, the galaxies, the molecular clouds and stellar nurseries, and the whole slow machinery of a universe-building complexity, is not universal. It is local. It is something that happens in some places and not in others. The universe, for all its extraordinary richness, contains within itself enormous regions where almost none of that richness is present. Where the cosmos chose, for reasons that sit at the intersection of the deepest unsolved problems in physics, to leave almost nothing. The void does not threaten us. It will not expand to consume us on any timescale that matters to anything alive today, or to anything that will be alive in any future we can meaningfully imagine. It sits in its place in the universe quietly, as it has for billions of years, doing what voids do, expanding slowly, pushing matter outward, playing its role in the vast and intricate machinery of cosmic structure. But it asks a question that science has not yet fully answered. Why is it there? Not just there in that region of sky, in that direction, in that part of the observable universe, but there at all. Why does a void this size exist in a universe that, by all our best models, should not have had time to produce it? Is it a statistical accident, a rare but possible fluctuation in the distribution of matter, unremarkable except for its size? Something the universe was always going to produce somewhere, and we happen to be in the part of the universe close enough to observe it? Is it a signature of the early universe that our models haven't captured? Some process, some condition, some physics operating in the first moments after the Big Bang that seeded this particular region with an underdensity so deep that 13.8 billion years of gravitational evolution turned it into the void we see today? Is it connected to the cold spot in the ancient light of the Big Bang? A mark left in the cosmic microwave background by the same primordial emptiness that eventually became the largest nearby structure in the observable universe? Is it telling us something about dark energy, about the way the universe's accelerating expansion behaves differently in different places, amplifying some voids and suppressing others, creating an uneven texture in the fabric of space-time that our uniform models haven't accounted for? Or is it something else entirely, something we haven't thought of yet? Something that, when we finally understand it, will seem obvious in retrospect, the way all good explanations eventually do. We don't know. That is the most honest answer available. We have mapped the Boötes void. We have measured it, argued about it, built theories around it, and refined those theories as better data arrived. We know it is there. We know its rough dimensions. We know what it contains, which is almost nothing, and we know, based on everything else we understand about the universe, what it should contain. We do not know why it exists in the form it does. The question sits at the intersection of cosmology, the physics of the early universe, and the still unresolved mysteries of dark matter and dark energy, three of the deepest unsolved problems in all of modern science. It will not be answered by one observation, one experiment, one flash of insight. It will be answered, if it is answered, slowly, through the accumulation of better maps, better measurements, better models, through the work of people who are, right now, spending their careers pointing instruments at this corner of the sky and trying to read what the universe is saying. In the meantime, the Boötes void remains what it has always been since the night Robert Kirshner's team first noticed the galaxies had stopped. A place in the universe that the universe itself seems not to have fully explained. 330 million light-years of silence. 330 million light-years of almost nothing. Waiting, in the direction of the herdsman, for an answer that hasn't come yet.